All right, here's our circular motion review. We have a designer wanting to build a roller coaster that has a horizontal loop where they feel an acceleration of 40 meters per second squared. That is going to be our acceleration. If the roller coaster has a speed, is traveling at 20 meters per second, what's the radius it has to have? All right, so we're going to use centripetal acceleration as v squared over r. We'll plug in our numbers. So 40 is equal to 20 squared over the radius. We want to solve for the radius. It's on the bottom, so we have to get it on top. We're going to multiply both sides by the radius. Gets rid of them over there. Now we want the radius that's on the top by itself, so we're going to divide both sides by 40. And so my radius comes out to be 20 squared over 40, or 10 meters. That's our radius. How long would it take the riders to complete an entire loop? That's asking for the period. That's what it means, how long to complete an entire loop. So we only have one formula with the period in it. That's 2 pi r over the period. So put in our numbers. The velocity is 20, is equal to 2 times 3.14 times the radius, which is 10 meters that we just found, divided by the period. Well, here the period's on the bottom. So we're going to multiply both sides by the period. And we want to isolate the period, so we're going to divide both sides by 20. It gives me the period is equal to 2 times 3.14 times 10 divided by 20, where the period is 3.14 seconds. You need to know how to do calculations like both of these. While going around a corner in a pickup truck, a young man feels like he's being pushed towards the outside of the turn. Explain to him why he feels that way. Use a diagram. All right, so for this fella, he is accelerating to the inside of the curve. That's what it means to have centripetal acceleration. When you accelerate, you feel a force opposite, or you feel you are being pushed with the opposite direction force, in the opposite direction than the actual acceleration that you have. This is an effect of inertia. So if we want to look at a diagram for that, here's our curve. That's the path that this young man wants to take. But if he's in the car going around the curve, that's where he's actually going to be, because the car has pulled him around it. He wants to be here. He is there. So he feels that effect. He feels the effect of being somewhere that he doesn't want to be. Number 10, we have a Viking swinging a mace over his head in a clockwise circle. The speed is 8 meters per second. The chain is 0.6 meters long. Is this a rotation or a revolution? This is a revolution. Sorry about that. I wrote down the wrong thing. This is a revolution because he's going around some center point. Sorry for the confusion there. Make sure we don't make that mistake. To get the period of the mace, we're going to take the velocity, which is 2 pi r over the period. We're going to plug in our numbers. So 8 meters per second. And then 2 times 3.14 pi times our radius of 0.6 divided by the period. So we're going to multiply both sides by the period. We're going to divide both sides by 8 to get the period by itself. And we see that the period is equal to 2 times 3.14 times 0.6 divided by 8. Or, move back over here, the period comes out to be 0.471 seconds. If I want the frequency of the mace, I know frequency is the inverse of the period, so I'm going to do 1 over the period, where the frequency of the mace is 1 over 0.471 seconds, or 2.12 hertz. I want the centripetal acceleration. Well, that's v squared over r. We've got the velocity, so that's 8 squared, divided by the radius of 0.6. Plug that into your calculator, and we end up with an acceleration of 106.7. What's the force of tension on the chain? Well, that's the only, meters per second squared. Tension is the only force acting, so I know net force is ma. I have all the numbers for that. It's 4, the mass of the thing, times the acceleration, 106.7. Well, the net force is 426.8 newtons, but there's only one force acting on the chain. So my net force is also the force of tension. So what I found for my net force, 426.8 newtons, is equal to the tension on the chain. On the diagram, show the velocity, acceleration, and force vectors of the ball. Well, I know that the velocity has to be tangent. The force has to be towards the center, and the acceleration has to be towards the center. So we'll put the velocity on first. Velocity, 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 velocity. Tangent to the circle going clockwise. Acceleration is in towards the center, and the net force is also in towards the center. If the chain were to break at the bottom, what direction would the mace go? It would follow the direction of the velocity at the bottom. It would continue in the same direction, in the same straight line path of the velocity that it had beforehand. So it would move to the left, horizontally, perfectly horizontally. Number 4, while we're on a luge run at the Olympics, the sled rounds a horizontal curve of radius 6 meters with speed 20 meters per second. I want to know the centripetal acceleration of the sled. Well, centripetal acceleration is v squared over r. I've got the velocity, that's 20 meters per second. We're going to square it. We're going to divide it by the radius of 6. So that centripetal acceleration comes out to be 66.7 meters. If I want the normal force exerted by the track on the sled, we're looking at force, so we have to do net force equals, one of them is net force equals ma, so that's 120 times 66.7, so that net force comes out to 8,000 kilonewtons. But I also know there's only one force acting on this horizontal circle, and that's the normal force. That's the track pushing on the car. We're on the sled in a circle. So what I know because of that is that the normal force is equal to my 8,000 Newton net force. That's what we get. Number 5, an object moves in a circle counterclockwise as shown. Ignore gravity. At point A, the force on the object is towards the center. Forces in a circle are always towards the center. They point to the center. So at point A, that's to the left. The force is going to be to the left. At point A is the velocity, left, down, upper, right. Well, the velocity has to be tangent to the circle. And so the velocity is going to point along the edge of the circle in the direction of the velocity. Sorry about that. In the direction of the velocity of motion, which means in this case it's going to be up. That's which way the ball is moving at that point. That's which way, if we cut it, it would continue to move. At point A, the acceleration of the object is also towards the center. Sorry, wrong way. The acceleration of the object in a circle is always towards the center. So in that case, it's just like the net force, and it's to the left. All right, we did the water cup demonstration. You want to know why the water remained inside the cup? The water at the very top had a high sideways velocity. So at the top, So at the top of the swing, the weight on the water was down and the tension from the bucket were both pulling down on the water. But it was accelerating down. That's what it means. All the forces acting on the water were down. The water had to be accelerating down. But the water was also moving sideways with some velocity. So the water did not fall because it was moving sideways very fast. All of the forces, all of those downward forces wouldn't make the object fall, wouldn't make the water fall or accelerate down, but all of those forces acted to just turn the water a little bit.